All right, so in this second lesson for Unit 4, we're going to be talking about some of the basics behind probability rules. And so with that being said, there's going to be quite a few definitions in this section, as well as quite a few different rules that you're going to have to write down to make everything kind of make sense. So you may end up having to pause this video a few times in order to be able to get everything copied down, and that's okay. So let's start with a few definitions, with theoretical probability first. So a theoretical probability is a probability which is based on a mathematical model. So not from observation. Like with a theoretical probability, we would say that the probability of flipping a coin and getting heads is 1 out of 2. That's coming from a mathematical model because we know that there are 2 possible outcomes and 1 out of those 2 is heads. Or let's think about rolling a dice. So if you were to roll a dice, there are 6 different sides on that dice. We would say the probability of rolling any of those numbers on the dice is 1 out of 6 because there's 1 outcome that we want and 6 total outcomes. So a theoretical probability is what you think of as a probability when you think about kind of what do we expect to happen. A subjective probability is a little bit different. So a subjective probability is your own personal assessment of your chances. It's not necessarily based on long-run behavior. In other words, this is what you would think of as like a personal probability. And you probably use these more often than you think. Like I might tell my wife that there's a 60% chance right now that I'm going to be taking a nap when I come home. Now that 60% is not based on mathematics, it's not based on long-run behavior. It's just, to me, I feel like it's about a 60% chance of me taking a nap. Or you might say it's a 50-50 chance of you showing up to an event. That means that you're about halfway going, halfway not going. You're not quite sure just yet. Or if you say that there's a 99% chance that you show up for practice, that means that you're pretty certain that you're going to be showing up for practice, barring any kind of setbacks that might occur. So this is just something that you kind of would say out loud to a friend or to someone else. That's really not based on mathematics, but more just your own personal assessment. Lastly, a probability model is going to describe all of the possible outcomes as well as the probabilities for each. So this is going to be important. We're going to be talking a lot about probability models today, what makes them appropriate versus not appropriate, and kind of how they work. So let's take a look at an example of this. Let's imagine we're going to flip a coin 3 times. Let's describe the probability model for this chance process and then use that to find the probability of getting at least 1 head in 3 flips. Okay, so let's first just list off our sample space. So let's list off kind of what are the different possibilities we can have when we toss a coin 3 times. Well, I guess one possibility is that you get heads all 3 times. Another possibility would be getting heads twice and then tails on the last flip. I suppose you could also get heads twice with tails on the second flip, and then also heads twice with tails on the first flip. We could also do the same thing with tails, so we could have 2 tails and then a heads, tails, heads and then tails, and then finally we could have heads, tails and then tails. Finally, we're going to have one last possibility, which is the possibility of having 3 tails in a row. So that would be tails, tails, tails. All right, so that's our sample space. Let's next talk about a probability model. And since we're interested in the number of heads, then let's go ahead and do it based on the number of heads. So here's an outcome with 3 heads. These are outcomes with 2 heads. These are outcomes with 1 heads, and this is the only outcome that has 0 heads. So in terms of a probability model, let's list off those different outcomes that are possible. So 0 heads, 1 heads, 2 heads, and 3 heads in 3 coin flips. We're next going to list off the probabilities for each of those. Now, if you count those up, there are a total of 8 possible outcomes. There is only 1 of those 8 outcomes which ends up having 0 heads. So that would be a 1 out of 8 probability. For 1 heads, there are 3 different outcomes that are possible out of the 8 total. So that would be a 3 out of 8 probability. For 2 heads, that is also going to be 3 out of 8. And for 3 heads, that would be 1 out of 8. So then there would be our probability model. If you want to convert those to decimals, that works. A lot of times you'll see them written as decimals, but fractions are okay too. So now we want to know, what is the probability of getting at least 1 heads and 3 flips? So that would mean getting 1 heads or 2 heads or 3 heads. So we want to know, what is the probability that at least one of those happens? So to figure that out, we could look at our table and see that that would be taking 3 out of 8 plus 3 out of 8 plus 1 out of 8. In other words, there is a 7 out of 8 chance that you're going to get at least 1 heads and 3 coin flips. So a pretty good likelihood that that's going to happen. Now, what we actually did was we actually used a rule there that we haven't talked about. And we need to be careful with that, because the rules, while they are simple, there are certain criteria that must be met when you are wanting to combine probabilities together. So let's talk about that. We're going to start by talking about some special types of events and their notation. The first is what are called mutually exclusive events or disjoint events. So these are events that have no outcomes in common. In other words, they cannot happen simultaneously. In other words, if you wanted to know what is the probability that it rains today, and also the probability of it not raining today, those would be mutually exclusive. We wouldn't say that it rains today and it also doesn't rain today. Either it rained or it didn't rain. You can't necessarily put those together. Or maybe you're flipping a coin and you want to know, what is the probability that we get heads and tails? Well, you're either going to get heads or you're going to get tails. You can't possibly get both. Even if the coin lands on its side, it's not really technically heads or tails. And so mutually exclusive events are events that do not have any outcomes in common. A little bit different from independent events. So let's talk about how independent events are different. So independent events are where one event does not lead to the next event being more or less likely. In other words, an example of independent events would be, what is the probability it rains versus what is the probability that we're able to have our basketball game? Now, here at North, obviously we have the field house, and obviously it raining is not going to have any sort of impact on whether or not we can have our basketball game. So those would be 2 independent events. So raining and having the basketball game would be independent of each other. They do not depend on each other whatsoever. Now, that's different from dependent events. So dependent events is where one event that's happened does actually lead to the next event being more or less likely. In other words, if we thought about the event of it raining and the event of having a football game, now it's a little bit different, because depending on the amount of rain and lightning and all of that sort of stuff, we may or may not be able to have our football game. So the ability to have the football game does depend on whether or not it rains, whereas the event of having the basketball game does not depend on whether or not it rains. So that would be the difference between independent and dependent. Again, the independent would be raining in the basketball game. Dependent would be raining in the football game. Now, obviously, we can come up with quite a few more examples than just that, but those are 2 pretty simple examples that would explain the difference between the 2. Finally, let's talk about the difference in a couple of notations that we're going to be using. We're going to be using and or pretty frequently when we talk about probabilities. As far as notations go, and is going to be written with an upside down U, or is going to be written with a normal U. Now, the reason for that or is what's known as the union. So we use U and union to represent that. For and, we just do the opposite of that. There is no kind of other way to remember it. It is the intersection, but that really doesn't go with the upside down U. One thing I've always kind of remembered is that and, you could put a line through the U and make it look like an A, whereas or, you just have to remember as being the regular U. So an and probability is that both events happen. So there's an intersection, they're both happening at the same time. Or is where one event happens, or the other event happens, or they can both happen at the same time. So or is what's known as inclusive. It's that one event can happen or the other or both. Whereas and is strictly that both events happen. It's probably best to describe this using a Venn diagram. We're all familiar with Venn diagrams, so let's talk about Venn diagrams and how they can illustrate some of these events. So in the space below, we're going to draw two Venn diagrams, one with events that are mutually exclusive, which I'll do in blue, the other with events that are not mutually exclusive or not disjoint, which I'll do in red. So remember, mutually exclusive, the events are not going to share any outcomes in common. So when you draw those events, like here would be event A, there cannot be any overlap with event B. So you've got two totally separate events, A and B. There is no overlap between the two. So really there is no intersection, so there would not be a way to do an AND probability for these two events. Otherwise it would be 0. Whereas events that are not disjoint, meaning they are not separate from each other or not mutually exclusive, means that there is going to be an overlap in between the two. So you've got event A, you've got event B, and then you've also got the possibility of A and B occurring simultaneously. That would be an example of AND. So AND would be the intersection. So that would be that section right there, which I'll just use the word AND in the notation for that to say that that would be what the intersection looks like. Or it would actually be the combination of both. So it would be kind of the entire area of A and B put together, and it would be not what was outside of those. Okay, so let's talk a little bit more about the probability rules that we're going to be using in this section and in later sections. First, we need to make sure that we understand what probability notation looks like. So probability notation is written with a capital P in parentheses and X with parentheses. It looks a little bit like function notation, with the difference being that instead of a function, we use capital P to say probability. Now, what is in parentheses is what's known as the event. A lot of times we'll use X to represent that. And so when we read it out loud, we'll say the probability of X. Now, obviously, we can put different things in the parentheses. For example, if we maybe said probability of H, that might be saying that the probability of heads is 0.5. Or we could say the probability of rolling a 1 on a 6-sided dice is 1 out of 6. So whatever is in the parentheses is the event, and then you list off what the probability is after it. All right, so let's talk about these rules. So rule number 1 says that 0 is less than or equal to P of X is less than or equal to 1. Let me say this in a little bit more simple terms. What this rule is saying is that every single probability has to be between 0 and 1 inclusive. In other words, you can't have a probability that's 1.7. That would be like 170% chance that something happens. Well, we're not going to use that. There is no such thing as a 170% chance. There's also not such a thing as a negative 12% chance. There is such a thing as a 100% chance, so that's why we're including 1. There's also such a thing as a 0% chance. That's why we're using 0. But every single probability has to fit between 0 and 1. Next is what's known as the probability assignment rule. That says that the probability of your sample space S has to equal 1. To give you an example of this, let's say your sample space was a coin flip, so heads and tails are your two outcomes. Then the probability of your sample space, in other words, the probability that you get heads or that you get tails, well, heads is 50%, tails is 50%, so the probability that you get at least one of those two is 100%. In other words, the probability of our sample space has to equal 1. In other words, if you were to add up all of the probabilities, they have to always add up to be 1. They have to add up to be 100%. Going back to our example with the 3 coin flips, if you think about it, going back and looking at our 4 probabilities, we had already added 3 of them together is 7 out of 8. If you add 1 more, then the probability of our entire sample space, 7 out of 8 plus 1 out of 8, has to equal 1. All right. The third rule talks about what's known as the complement of an event. So the probability of X complement is, in other words, just saying the probability of not X happening. In other words, if you wanted to say the probability that it doesn't rain, then that you could say the probability of rain complement, that would be the probability that it does not rain. So it's just a simple way for us to say the probability that something doesn't happen. Now, in order to calculate that, we have this nice formula, which is that the probability of x complement has to equal 1 minus the probability of x. In other words, if you want to know the probability that it doesn't happen, just take 1 minus the probability that it does happen. All right, rules 4 and 5. We're now going to get into at least some of the rules that we're going to be using frequently. In fact, we've already used one of these rules, although we needed to be a little bit more careful. The one that we've used already is the probability or the addition rule. So the addition rule says that the probability of A or B happening is that you take the probability of A plus the probability of B. Now, where you need to be careful is that A and B have to be disjoint, or they have to be mutually exclusive, meaning they cannot happen at the same time. There cannot be an overlap between the two events. So where we used this was back here on this first example where we were flipping a coin, and we wanted to know what is the probability that we get at least one heads. In other words, the probability that x was greater than or equal to 1. Now, in order to calculate that, we added together 3 out of 8 plus 3 out of 8 plus 1 out of 8. Where we needed to be careful was we needed to be able to say that those events were disjoint. In other words, the probability of getting 1 heads is not going to overlap with any of the probabilities of getting 2 heads, and that wasn't going to overlap with any of the probabilities of getting 3 heads. And that is in fact true. You either got 1 heads, or you got 2 heads, or you got 3 heads. There's no way for you to get both 1 heads and 2 heads in a single trial. And so there were disjoint events, and so we were okay to add those together. We just need to make sure we're careful in the future that we're always checking to make sure that they're disjoint first. Next is the multiplication rule. We haven't used this rule yet, but let's talk about it. If you want to find the probability of A and B both happening, then you'll take the probability of A multiplied with the probability of B. Now, in order for this rule to work, A and B must be independent. In other words, they cannot depend on each other. Lastly, there's going to be some times where you're asked, especially in the homework and on the quiz on Friday, whether or not the rules or whether or not it is a legitimate assignment of probabilities. In order to do that, you need to check rules 1 and 2. In other words, you need to check to make sure that all of the probabilities are between 0 and 1, and also that they all add up to be 1. In fact, let's take a look at an example of this. So let's say we were to randomly select a student who took the 2010 AP Stats exam, and we're going to record the student's score. Here's the probability model. So on the exam, you can either get a 1, 2, 3, 4, or 5. The probabilities are listed below, and it wants us in part A to show that this is a legitimate model. In order to do that, the first thing we have to decide are all of the probabilities between 0 and 1. In other words, if you look at all of those probabilities, are there any that are below 0? And no, they're all positive. Are any of them more than 1? And no, they're all less than 1. So yes, that first rule is met. They are all between 0 and 1. The next rule that we need to check is that the probability of our sample space adds up to be 1. In other words, if you take 0.233 plus 0.01 or 0.183 plus 0.235 plus 0.224 plus 0.125, what do those all add up to be? And if you type those into either your phone or a calculator, you'll find that they do in fact all add up to be 1. So yes, this is in fact a legitimate probability model. For part B, let's find the probability that the chosen student scored a 3 or better. So first thing we're going to do is write that out as a probability. So we want to find what is the probability that the student, which we're just going to call X, got a 3 or better, so is greater than or equal to 3. So greater than or equal to 3, we're going to add up these 3 values right here. And if we do that, if we take 0.235 plus 0.224 plus 0.125, those are going to all add up to be 0.584. In other words, there's about a 58% chance the student got a 3 or better. All right. For the last part, for part C, find the probability that the chosen student didn't get a 1. So this would be an example of using the complement. So remember, to say that they didn't get a 1, is to say the probability of one complement. Now, in order to find that, the probability of one complement is that we're going to take 1 minus the probability that they did get a 1. In other words, taking 1 minus the probability of getting a 1, which would be 1 minus 0.233, which is 0.767. In other words, there's a 77% chance or so that they didn't get a 1, meaning that they got a 2 or a 3 or a 4 or a 5. Now, I suppose the other way you could have worked that is you could have just added up 2 plus 3 plus 4 plus 5, and you could have gotten the same answer that way. But it's a little bit quicker to use the complement rule and just take 1 minus that probability. Let's take a look at one more example and we'll be done with this section. So the traffic light at Johnson Drive and Broadmoor Street has the following distribution of traffic signals when you're traveling east on Johnson Drive. So the probability that you get a green light is 0.35. The probability that you get a yellow light is 0.04. They did not include the probability that you get a red light. But we should know that this probability all have to add up to be the number 1. So when it asks us to fill in the missing probability, if we take 1 minus the probabilities that we already know, so that would be 1 minus 0.35 minus 0.04, that's going to tell us that there is 61% left over. In other words, there's a 0.61 probability that you end up at a red light. So then, what is the probability that the light is not green when you get to the intersection? We can really do that 2 different ways. So let's talk about those 2 methods. The first, when we think about not green, you should probably be thinking about the complement rule. So the probability of getting a green light complement or not getting green. Remember that we can find that by taking 1 minus the probability that you get a green light, which would be 1 minus 0.35, which is 0.65. Now, the other way we could work through this same problem is to think about what it means to say that the light was not green. Well, if it's not green, then it would have to be yellow, or it could also be red. So we want to find what is the probability that it's yellow or red. Now, remember for the or probability, we're going to be using this addition rule. In order to do that, though, remember that A and B must be disjoint. In other words, we need to check and see before we add these together, is it possible to have both a yellow light and a red light at the same time? And no, obviously the light's either going to be yellow or red. It's not going to be both at the same time. So we are okay to go ahead and add those probabilities together. If we take 0.04 plus 0.61, those add up to be 0.65. And that is, in fact, the same as the probability that we found before. So 2 different ways of getting the same answer. Okay, for part C, what is the probability that you find the light to be red on back-to-back days? So we want to know what is the probability that it's red on the first day. I'm going to just call that R1. And it's also red on the second day, so R2. Now, for an AND probability, remember that that is where you're using the multiplication rule. So the multiplication rule, we're going to take the probability that it's red on the first day, multiplied by the probability that it's red on the second day. Now, once again, we need to check something. Remember, in order to use the multiplication rule, the events have to be independent. In other words, does knowing that the light was red on the first day affect the light being red on the second day? And I would say no. Having a red light the first day, that's not going to have any impact on it being red the second day. So we should be good to go ahead and multiply those together. So we'll take 0.61 multiplied by 0.61. And when we multiply those together, we get 0.372. In other words, there's about a 37% chance that it's going to be red on both days. Okay, so for the last one, for D, what is the probability that you make the light all week after leaving school? Okay, well, the probability that you make the light would have to be that it was either green or that it was yellow. So when we want to find those, we're going to add those together. Again, remember, it cannot be both at the same time, so we are okay to go ahead and add those. So 0.35 plus 0.04 is going to be equal to 0.39. Now, remember that that's just for making it one day. But if we want to find the probability that it's going to be that you're going to make it every single day, you're not going to have to just make it once, but you're going to have to know what is the probability that it's green or yellow 5 times. In other words, green or yellow multiplied by itself 5 times or to the 5th power. In other words, we're going to take 0.39, raise that to the 5th power, is going to be 0.009. So a very, very small probability. So you're probably not very likely to make that light every single day after school, less than a 1% chance of that happening. All right, guys, that is it for this section of the notes. In the next section, we're going to look at a couple of structures that we can use to help us illustrate probabilities, which are called two-way tables and tree diagrams. Until then, have a great rest of your day.